Hello, welcome. This is the first part of my lecture, and in this video, I'm going to talk about the background, especially about why we need to define the minimal surface entropy and why we are interested in this quantity. And then we will move on to some main results. More precisely, when you have a three-dimensional hyperbolic manifold, then it was proved by category Marquez and Nevis that we are able to evaluate the minimal surface entropy in the hyperbolic case. And moreover, that number is rigid, meaning that if you have another metric that has the same minimal surface entropy, then the metric should be isometric to the hyperbolic metric. And inspired by that, I was able to extend the result to some higher dimensional case when the dimension of the hyperbolic manifold is an odd number. And I'm also going to go over the theorem, and the proof will be contained in the next video. So if you are interested, feel free to click on my second part of the video. Okay, now let's start with the motivation part. Here, I want to mention a classical result given by Dyson, Callaway, and Gallot that if we have a closed hyperbolic metric, closed hyperbolic manifold of dimension greater than or equal to 3, and suppose we have another metric H which has negative sectional curvature and it has the same volume as in the hyperbolic case. Then if we consider the volume entropy with respect to H, it can be computed by this equality. Here, that is equivalent to count the number of geodesics with respect to H. Okay, then their result was to say that the volume entropy of H must be greater than or equal to the volume entropy of H naught, the hyperbolic case, which the latter one is equal to n-1. Moreover, this number is rigid, meaning that the equality holds if and only if H is isometric to H naught. Okay, now from their result, they look at the geodesics. Like they use the number of geodesics to measure the volume entropy. And here the geodesic is a one-dimensional local minimizer because in the local picture, it minimizes the length of the curve. So this is a 1D local minimizer. So it's natural to ask if we can extend this result to some higher dimensions. For example, can we discuss this result when dimension is equal to 2? So we are going to look at the 2D local minimizer. In dimension 2, we're going to look at the area of the surface. And if you are familiar with these concepts, you should know that the two-dimensional local area minimizer is exactly the minimal surfaces. Okay, and in the previous result, they discussed the comparison result related to the volume entropy of H by counting geodesics. So here we wanna, like, I was wondering if there's a quantity, some other entropy to count the number of minimal surfaces in M. So that's why the authors define the minimal surface entropy. Okay, now before moving on to the theorems, I want to introduce some basic notations. First, we are going to focus on the closed manifold M, whose dimension is greater than or equal to 3, and it has a hyperbolic metric H0. So regarding the hyperbolic manifold, they can be denoted by Hn, the n-dimensional hyperbolic space mod some discrete subgroup. Okay, and secondly, the minimal surface is a surface whose mean curvature is equal to 0, and in the local picture, it minimizes the area locally. Okay, and now we say the surface is essential if we have the following properties. Here, the surface sigma g means that we have a surface in M whose genus is equal to G. And it is essential if the injection from sigma G to M induces another map on the fundamental groups, and this map is injective. Okay, moreover, we can see the image of ester of pi 1 sigma G is a surface subgroup in gamma of genus G. Okay, and apart from these notations, here I will also want to mention a classical result given by Shen and Liao. This is very useful in our talk. In the metric M, suppose we already have an essential surface sigma G. Then the result size, so from here, it corresponds to a surface subgroup pi. Okay, and from here, the result says that there must exist an area minimizing surface S that is homotopic to sigma G. And to be clear, I also want to say that the inclusion from S to M is a branched inversion. In particular, when the ambient dimension of M is equal to 3, we are able to say S must be immersed in M. That was proved by Osman and Gulliver. But unfortunately, when the dimension is equal to 4 or even higher, we don't have a similar result. That is to say, M might have some branch points. Okay, now our essential minimal surface S also corresponds to some surface subgroup, and that is conjugate to pi by some element in gamma. Okay, now to introduce the minimal surface entropy, I also want to give you some further notations. Here we define the set S parentheses mg to be the equivalent classes of surface subgroups of genus less than or equal to G, up to conjugacy. More precisely, inside of that set, we define the subset as mg epsilon. Here, epsilon can be any number greater than or equal to 0. We define this to be a subset that contains elements in the previous set whose limit set is a 1 plus epsilon quadricircle. Okay, now I'm going to introduce what is a limit set and what is the 1 plus epsilon quadricircle. Firstly, for the limit set, we know that in the Poincare model, the n-dimensional hyperbolic space can be considered as the ball of the unit ball of dimension n, and the boundary at infinity is the n-1 sphere. Okay, now the limit set related to pi is a subset of the n-1 sphere that contains the accumulation points of the orbit of pi x. X can be any point in Hn. And I also want to mention that the limit set of pi is independent of the choice of x, meaning that like no matter what x we are taking, the limit set is identical. And secondly, we say the limit set is a 1 plus epsilon quasi-circle if there's a 1 plus epsilon quasi-conformal map that sends the round circle to the limit set. To help you understand, I can draw the picture. Suppose we have this hyperbolic ball, and initially we can take the round circle. Okay, and in this talk, we always assume epsilon is a sufficient small positive number. So in that case, a 1 plus epsilon quasi-circle can be like this. It can be pretty weird, but that must be, it has more perturbation from the round circle. This is a 1 plus epsilon quasi-circle. Okay, and here for our set, if epsilon is taken to be 0, that is to say the limit set must be a 1 quasi-circle, and that's exactly a round circle. And we know that for the round circle, it corresponds to a totally geodesic disk. So after mod the like pi 1m, it corresponds to some essential totally geodesic surface in M. Okay, so but for hyperbolic metric, it doesn't have to like contain any totally geodesic essential surface. So when epsilon is equal to 0, the set of SMG0 can be empty. However, when epsilon is positive, the set is always non-empty. And actually, it was evaluated by Ken and Markridge that this number, the number of candidates in this set is comparable to the constant number, the constant times g to the power 2j that depends on the genus G. Okay, that's our set as mg epsilon. And if we take the union of all the genus G, we get this larger set S sub epsilon m. Okay, now thanks to all the notations, we finally were ready to define the minimal surface entropy. Here, we define the surface in the following way. We take the limit as epsilon goes to 0 and as L goes to infinity. And in particular, in the numerator, here, area with respect to h of pi means we take the area of the area minimizing guy inside of the homotopy class of pi. Okay, and I also want to mention the uniqueness result proved by Uhlenbeck and Seppi separately, that when we have a closed hyperbolic 3 manifold, then if epsilon is taken to be small enough, then in any homotopy class, there's only one minimal surface. And that is to say, like in our definition of the minimal surface entropy, to count the number of equivalent class of the homotopy classes, that's equivalent to count the number of minimal surfaces. And that's also why we call the entropy minimal surface entropy. Okay, and now direct corollary. We are going to say that this quantity on the numerator, the number of minimal surfaces whose area is bounded by 4 pi L minus 1 is comparable to a multiple of L to the power 2L. So after taking the natural log and divided by L natural log L, and we take the limit as L goes to infinity, we can say that this is for the hyperbolic case. Then we can say that the hyperbolic entropy of hyperbolic metric is equal to 2. We are going to say the proof. Okay, now I want to introduce some main theorems. First, we look at the results for dimensional 3. It was proved by Calgary, Marcus, and Navis that the entropy of hyperbolic metric is equal to 2. Secondly, if H is another remaining metric on M with section curvature less than or equal to 1, then the entropy of H must be greater than or equal to 2. And the equality holds if and only if H is isometric to the hyperbolic metric H0. Okay, and recently, Low and Navis show that, on the other hand, if we have another metric whose scalar curvature is greater than or equal to -6, then the minimum surface entropy is even smaller. That's less than or equal to 2, and this is also rigid. But in this talk, we only focus on the case where the sectional curvature is less than or equal to 1. Okay, now, inspired by theorem 1, I was able to show in the higher dimensional cases, when n is an odd number, then the minimum surface entropy of hyperbolic metric is also equal to 2. That is independent of the ambient dimension. And also, if H is another metric which has sectional curvature less than or equal to 1, then it has entropy equal to 2 or larger. And also we have this rigidity result. Okay, then in the next video, I'm going to talk about the proof of theorem 1 and theorem 2.